Okay, so let's get into this last section of notes here. We are still in Unit 7, and we've been talking about quadrilaterals, or in other words, these different types of four-sided shapes and all this information that we know about them. So today we're adding our last one here. This is going to be 7.5 trapezoids, and the date that we did this would be the 22nd. Objective for today is we're basically doing the same kinds of things we've seen before. We're introducing a new type of shape, and then we're using information about it to solve for different measurements and variables and so on and so forth. Okay, so first off, what is a trapezoid, and how is it different from the other shapes that we've talked about in this unit here? So a trapezoid is a type of quadrilateral, okay, a type of quadrilateral that has exactly one pair of parallel sides. One pair of parallel sides. Okay, so notice this is different from the types of shapes that we've seen before, because everything up to this point we've talked about parallelograms where there's always two sets of parallel lines. In this case, a trapezoid is just one. So for example here, we're trying to see what this looks like. I'm going to draw these lines here. I'm going to draw one line on the top and one line on the bottom, and those are going to be our parallel lines. So I'll go ahead and mark those with the arrows as well. Okay, so this would be an example of a trapezoid. Usually you kind of see it kind of looks like a triangle if you took just a top piece off. Okay, so notice we only have one pair. The other pair of opposite sides are not parallel here. And then we also have some names for these as well. So the two sides that are not parallel, so eventually they would intersect, these two sides are what we call the legs of a triangle, or not of a triangle, but of a trapezoid. Okay, these are the legs of the trapezoid. And then the other two sides, the sides that are parallel, we have a name for those as well. Those are what we call the bases, or each of those is a base of those triangle. Or I keep saying triangle, trapezoid, excuse me. Okay, so these are the two pieces that we need to pay attention to, the legs of a trapezoid and the base, or the bases of a trapezoid. Okay, one other term that you want to be familiar with, because we're going to include this in one of our properties, is what we call our base angles. So our base angles here, okay, are just a pair of angles that are, and let me rewrite that here, that are, simply put, are on the same base. That are on the same base. Okay, so for instance, if I'm looking at this picture that we've drawn here, let's say we call this, I'll go ahead and label this as well, trapezoid ABCD. If this is a trapezoid and we're talking about the base angles, I want the angles that are on the same base. So for example, we'll keep it simple and just name it with one letter. Angle A and D, I'm not going to mark these with arcs, but angle A and D would be a pair of base angles. They're on the same line that specifically is parallel to another side. So that's one pair of base angles, and then same thing here. On the other piece, angle B and angle C would also be an example of base angles. And we'll talk about what we know about them here in just a minute, but just want to understand what that term means when I use that. Okay, angles that are on the same base. Notice D and C would not be base angles, and A and B would not be base angles, because they're both on the same legs, but not on the same base. Okay, and then the last one specifically, a type of trapezoid that we're really going to focus on, because we know information about it, is what we call an isosceles trapezoid. Okay, an isosceles trapezoid. And you could actually kind of take a guess at what this would mean, because we've seen that word isosceles before when we talked about triangles. Remember, isosceles triangle is a triangle that has two congruent sides. Okay, an isosceles trapezoid, same kind of thing here. It's a trapezoid with two congruent sides, but specifically, this is a trapezoid whose legs are congruent to each other. Okay, specifically, an isosceles trapezoid is a trapezoid whose legs are congruent to each other. So for example, if we were looking at that trapezoid that we drew for the definition here, that would be AB and DC. They have to be the same length. Okay, and this is helpful because if something is an isosceles trapezoid, then I know some different properties or pieces of information about it. Okay, so let me write this down here. If a trapezoid is isosceles, so specifically it has to be isosceles, it can't just be any trapezoid. But if it's isosceles, then we know two things. Okay, the first thing that we know is we can say that the base angles are congruent. The angles that are on the same base are going to be congruent to each other. So for example, I'll go ahead and draw another trapezoid. Again, this has to be isosceles, so let's say we have one set of parallel lines, and then the other sides, the legs, are going to be congruent to each other, so I'll mark each of those with a dash mark. And let's just keep this in order. Let's say it's E, F, G, H. Okay, if I say the base angles are congruent, what that would mean is angle E and angle F are on the same base. So angle E would be congruent to angle F. And then same thing here with the other pairs of angles that are base angles, angle H and angle G. Same kind of idea. Angle H is going to have to be congruent to angle G. And then as a reminder, one other thing that we know that we've talked about before is I know since this is a four-sided shape, all of these angles are going to add up to 360. So we can use that kind of information as well. That's the first one here. The base angles are congruent. And then second thing here as well that we know is I'm going to say, or I can say, that the diagonals are going to be congruent as well. If a trapezoid is isosceles, then one other thing I know is the diagonals are congruent. So this is similar to something we talked about when we talked about rectangles. So for example, if I'm looking at this here, if I draw these in, I have EG and FH, and I could say exactly that EG is congruent to FH here. Okay, so that's the idea with, with isosceles trapezoids specifically. Okay, so I'm looking at this here. Let's practice this a little bit. Okay, put this to use. Example 1, I want you to take a second. I want you to sketch all of this here. So notice we're told that this is a trapezoid, and the good news is that we wouldn't need to be told that because we already have that information. I have one pair of parallel sides, and then specifically one thing that's helpful as well is I see that those sides are congruent, which means this has to be an isosceles triangle. So now those couple properties that we just wrote down are going to apply here. So with this in mind, we want to use this first to find angle ADC. So if I draw this out here, angle ADC, if I'm thinking about how I could figure out that angle measure, and using the properties that we just wrote down, remember we said that the base angles are going to have to be congruent. So for example, if angle C is 101, it's going to have to be the same thing here. Measure of angle ADC is also going to have to be 101 as well. Okay, this would have to be 101 degrees. Okay? All right, and then the next one here that it asked us to find, and I'll just leave that label there, is angle CBA. So now if I'm looking over here, I'm asking how would I figure out what this angle measure is? There is multiple ways to go about this, but I'm still using this property that we just mentioned, which is that the base angles are going to have to be congruent. So for example, one way we could solve this is let's just call this angle that we're looking for X, since we don't know what it is yet. And if we're using that property, then I know angle A is going to have to be congruent to it, so I know that would also have to be X as well. Okay, I know those two are going to have to be the same, whatever they are. So I have this information, and then like I just mentioned earlier, since this is a quadrilateral, I know all four of these should add up to 360. And so I'm going to go ahead and do exactly that. I'll say 101 plus 101 plus X equals 360. So using what we talked about all the way back in 7.1, adding these up to 360. And now that I have this set up here, I can go ahead and just combine my like terms and solve. So if I combine my numbers here, I have 101 and 101. Add those to get 202, and then X and X is going to give me 2X, and then equals 360, and then we can just solve the rest here. So I could subtract 202 from both sides. When I do that, those cancel, leaving me with 2X here, and then I have 360 minus 202, that's going to be 158. And then last step here, divide by 2. These cancel out, and I'm left with X equals 158 divided by 2. And if I didn't know this, I could just type this into a calculator, but this is going to end up giving me 79. Okay, so X equals 79 here, and remember that was the angle that we were looking for, so measure of angle CBA, in other words, is going to be 79 degrees. Okay, so just make sure you're always double checking, do I need to plug it back in, or what was the question asking for here? So we found X, so we're good. Okay, so that's one way that you can use these to solve some different problems. Okay, another way that we can see this, using this to solve for a different property here, I want you to take a second, I want you to sketch this trapezoid as well. And notice, we have this here, we're given that this is an isosceles trapezoid. So this is helpful because, like I mentioned, all of these properties now apply. If we didn't have this, then we unfortunately could not set up any equations. Okay, so I'm given that this is an isosceles trapezoid. I'm told AC is 15 minus 3x, and then I'm told BD is negative 5 plus 23, and I want to find the length of AC. Well, if I'm looking at this and I'm trying to think about how I could set this equation up to solve for x, remember this is one of the other properties we just wrote down. We said the diagonals in these kinds of shapes are going to have to be congruent. So simply enough, I can just set these equal to each other. So we can say 15 minus 3x equals negative 5x plus 23. Diagonals have to be congruent. And now that we have this here, we can solve. Okay, there's multiple ways to go about this. My biggest recommendation to start this would be to add 5x to both sides so that I can get rid of those negative variables. I do on the left side, they cancel. I'm sorry, on the right side, they cancel. I have 15, and then I have negative 3x plus 5x. That's going to be a positive 2, and then equals 23. Okay, continue to solve. I can now subtract 15 from both sides. When I do that, I'm left with 2x. And on the right side, I have 23 minus 15. That's just going to give me 8. And then last step here, divide by 2. So I get x equals 8 divided by 2, which is 4. Okay, so first step is done. I can go ahead and circle that or underline it if I want. But as a reminder, we know a good habit to get into is always check, do I need to plug that back in? In this case, I do. And the good news is it doesn't matter which one I plug it back into because they're supposed to be the same length. Okay, but we'll plug it back into AC. So we were told that's 15 minus 3x, or in other words, now that we found x, that's going to be 15 minus 3 times 4. So AC here is going to equal 15 minus 12. And so my final answer is going to be AC equals 3. Okay, so make sure, only thing on there that you need to pay attention to is making sure that you plug your variable back in and find whatever that side length is. Okay, but simple enough. We've done problems like this before. We're just using this in different shapes. Okay, one other thing that we need to talk about here as well, because I know you guys know how to use the properties pretty easily, is how to show that something is a trapezoid. Okay, how would I be able to show that something is, or the shape I'm looking at is a trapezoid? So we have theorem 7.5, because again, we don't have a specific name for this. We're just going in the order of the ones that we've already done. We went through 7.1 through 7.4. So theorem 7.5, we can say this. We can say if a quadrilateral has exactly one pair of parallel sides. The quadrilateral has exactly one pair of parallel sides, and also if the diagonals are congruent to each other. If the diagonals are congruent, then what I can say here is I can say then the shape is an isosceles triangle. I'm sorry, isosceles trapezoid. Okay. If a quadrilateral has exactly one pair of parallel sides and if the diagonals are congruent, both these are met, then I can say that this is an isosceles trapezoid. So notice that first piece, the one pair of parallel sides, just comes from the definition of a trapezoid, and then the other piece is one of our properties that we've mentioned with isosceles trapezoids. And they found that if you have a trapezoid like this and the diagonals are congruent, then it has to be isosceles. There's no way that it cannot be. Okay, so we're going to use this because now we can see how would I be able to show that something is an isosceles trapezoid, and I want to make sure I fit the criteria for this theorem. Okay, so last example here, example 3. I want you to take a sec and I want you to sketch this graph for me here. Okay, and we notice this would be the y-axis here. I know it's not labeled for you, but you have this here, and then if you need to, you can add the dash marks in. That's 1, 2, 3, and 4. Okay, so given quadrilateral ABCD, I want to show that this is a trapezoid, and I want to determine if it is isosceles. So if I want to show that this is a trapezoid, remember we said the definition of that is I just need one pair of parallel sides. So I need to test, really, if I want to find if they're parallel, I want to test their slopes and make sure that at least two of them are the same. So for instance, let's start with the first side here. Let's just say the slope of AB. Okay, the slope of AB here. And we've mentioned this before. If I really want to, I could, I could do the slope formula, but since we have the graph, I know the slope is just rise over run here. So the rise is going to be 1, and then the run is going to be over 2. So rise of 1 over 2, so slope of 1/2. Okay, simple enough. If this is a trapezoid, then I need to make sure that that opposite side also has the same slope, because those should be parallel, right? So we say slope of CD here. Now let's look at this line and find the slope here. Again, we can just do rise over run. So we have a rise of 1, 2, and then a run of 1, 2, 3, 4. So I could say 2 over 4, which is going to come out to be 1/2. So I can put a check mark on those. That's one pair of parallel sides. One other thing I need to check is I need to check and make sure the other pair of sides that I haven't mentioned yet are not parallel, because otherwise this would be a parallelogram. So I need to make sure it has only one set of parallel sides. So to do that, I'm going to take my next side, slope of BC, and I'm going to find what that is. Same as before, I can just do rise over run. So if I'm starting at B, I can go over down 1, 2, 3, so a slope of -3 over the run, which is 1, 2. So -3 over 2 would be my slope here. And last one I need to find the slope of would be the last side, AD. Okay, and make sure that this doesn't match. So my rise here, in this case, I'm going to go down 1, 2. So I can say slope of AD, it's going to be -2 over the run, which is 1, 2, 3, 4. So that comes out to be -2 over 4, or if I want to simplify that, -1/2. Okay, so these two here are not the same, and so that's good. That means that this is a trapezoid, because I only have one pair of parallel sides here, AB and CD. Okay, so I'm going to say first off, this is a trapezoid, and I can mark it however I'd like. I'm just going to put trapezoid and put a check mark by it, just to remind myself. So I found that this is a trapezoid, but it says the second part here is I need to determine whether it's isosceles. Well, if I go back up to my theorem, I've got the first part. I've shown there's exactly one pair of parallel sides, but I also need to show that the diagonals are congruent in order for this to be isosceles. So if I want to find the diagonals here, if I look, I see I have one diagonal, which is AC, and I need to find the distance of that, or the length of that, because the lengths need to be the same, not necessarily the slopes. And then same thing here with the other diagonal as well. I have BD, so I need to find the length of BD and then see if these two come out to be the same, because if they both have the same length, then this is going to be isosceles. Okay, well, if we think back to how we'd find the length of something, the first one's actually pretty easy. If I find the length of AC, since this diagonal is just a line straight up and down, I can just count the boxes. So the length of AC here is just going to be 1, 2, 3, 4. Okay, so it makes it very simple. Okay, so this is the length of AC. I could just count that. It's not too bad. The problem with the other one is if I look at this other diagonal, BD, it is not just a straight line going left and right. And so what we're going to have to do is we're going to have to use what we've seen before, which is called the distance formula, so that I can find the length of this here, the length of BD. Okay, and just for those who don't remember, because I know it's been a while since we worked on the distance formula, the distance formula here is going to be distance equals this big square root symbol. And remember, that's x2 minus x1 all squared plus y2 minus y1 all squared. And as a reminder, this just comes from rewriting the Pythagorean theorem. So if I want to find the length of BD here, and I'm going to plug these in to these different values for x2, x1, so on and so forth, it's probably a good idea to mark where my points are at. So I have point B, that's at the point 1, 2, x coordinate of 1, y coordinate of 2, and then D is at the point here 7, 1, x coordinate of 7, y coordinate of 1. And now I'm just going to plug these into my equation and see what comes out. So I have the distance equals the square root of, I have x2, so the x coordinate of the second point is 7, minus, make sure it's minus, x coordinate of the first point, which is 1. So 7 minus 1, and then all squared here. Okay, and then plus, again, put parentheses around this, y2, so the y coordinate of the second point is 1, minus y1, which is 2, and then again, all squared. Okay, so now I've got them plugged in, and I just need to simplify this, and we will see if they come out to be the same or see if it comes out to be 4. So I have 7 minus 1, that's just 6, so I can just say 6 squared. And then the other one here, I have 1 minus 2, which is going to be negative 1. So I need to put plus, and I'm going to put negative 1 in parentheses since there is a negative, and then I'm going to square it. So now we can keep simplifying. I can square these here. I have 6 squared. Remember, that's just multiplying it by itself, so that's just 36. And then if I have negative 1 squared, remember, even though it's a negative, if I multiply it by itself, a negative times a negative is going to be a positive. So anytime I square something, that number is always going to come out to be positive. In this case, negative 1 times negative 1 is positive 1. So we have this here, square root of 36 plus 1. So this is going to come out to be the square root of 37. Okay, and we could type this into our calculator. This is not going to come out to be a whole number. But all we really needed to check and see is this the same length as AC? Well, notice AC was 4, and this was square root of 32. So this, I'm sorry, square root of 37. So this is going to be a trapezoid, but it is not going to be isosceles, because we said those would have to be congruent in order for this to be an isosceles trapezoid, excuse me. Okay, so that is our notes for today. If you have any questions with that, as always, feel free to let me know. Otherwise, assignment for today is 7.5 homework trapezoids, and that should be posted on the class website. All right, thanks, guys.